Hello, good morning. My name is Isa Babaadun. I'm master's degree student in electronics and electrical engineering at Üsküdar University, Turkey. Today I'm going to present a topic about electromagnetic waves, titled as Investigating Electromagnetic Radiation within People in Crowds. This study uses a novel multi-component discrete propagation model to analyze electromagnetic wave behavior in public and dense crowds relevant to 2G, 3G, 4G, and 5G technologies. Within our study, we focus on 4 key parameters: specific absorption rates are, electrical field, skin depth, and effective radiated power to assess real-world exposure scenarios. By simulating the impact of varying electrical field strength, this research provides valuable insights for radio frequency exposure guidelines, considering whole body SAR limits, and potentially guides the design of future devices that minimize emissions or target energy absorption in less sensitive buried areas. Despite use of telecommunication technologies and safety standards by International Non-Ionization Radiation Protection Committee, limiting the whole body SAR to 0.08, public concern persists regarding potential health effects of radiofrequency radiation. Are we within standard safe limit, or we exceeded the safe limit? This research addresses a gap in knowledge by investigating how human crowds affect electromagnetic wave behavior, providing a clear understanding of how the crowds interact with such waves. We will perform this work using discrete model. Discrete model introduces a novel radio frequency propagation model specifically designed for forest. As you can see below, this model treats forests as collections of individual scatterers, trees, and leaves. The model assumes that the forest is made up of identical scatterers, each with a specific volume, a dielectric, and a radius. Transformation. Human bodies, like vegetation, scatter and absorb waves to varying permittivity. Accordingly, since our simulation is based on human parameters, we modified needles to fingers, leaves to palms, branches to arms, and trunks to bodies. Theoretical aspects. Specific absorption rate measures electromagnetic wave energy absorbed by human tissues. It can be averaged over the whole body or a smaller volume like 1 gram or 10 gram. As you can see, this is the equation. Represents SAR, while E is electrical field, and sigma represents electrical conductivity, and rho denotes for mass density. Skin depth refers to depth at which amplitude of electromagnetic wave has decayed to approximately 37% of its original. This is equation of skin depth, while alpha is attenuated constant, or also can be called a real part of propagation constants. Effective radiated power, which is fixed for antenna and frequency, represents isotropic antenna power needed to match a specific antenna's strongest beam strength. In order to calculate ERP, we need to crossed by these equations of power density, while PT represents transmitted power, GT is the gain, and R is a distance from antenna. And from equation 5, we obtain the magnetic value of electrical field, from which we calculate ERP, effective radiated power. Simulation results. So in this section, what we did is we created crowd density from 2 people to 36, going through 4, 8, 12, and 32 people placed within the circle of 6 diameters. So we apply the electrical field to this density and see what happens to electrical field SAR and skin depth. As you can see, these are the lines of electrical field, or also we can say attenuated electrical field or absorbed electrical field. The red line is the free space electrical field, which means with no presence of density. So as you can see, electrical field changes with the change of density. The black returns to 2 people, while the green returns to 36 people. The first observation is within the blue line. You can see for the 8 people in the blue line, almost half of the electrical field has been absorbed, while the green line, almost all the electrical field is absorbed. So on our right is skin depth. The first observation is almost all the lines of skin depth are overlapped, which means skin depth does not change with a change of density. However, it decreases with the increase of frequency. This is the graph of specific absorption rate. There are 2 observations here. The first one is it changes with the change of the crowd density. As you can see, this is for 2 people and blue for 36 people. Second observation is it changes when the frequency changes, especially within the last 2 lines or 4 lines. On our right is we brought these graphs here for the sake to make comparison against the safety limit, which is 0.8. As you can see, we are still too far below the safety limit. In this section, we applied, or we can say we increased the electrical field and applied to 36 people to see what happens to skin depth and SAR. Another observation for skin depth, again, it does not change with the change of electrical field, and all the lines are overlapped. However, as usual, it decreases with the increase of frequency. On our right is the SAR graphs. You can see it exceeded the safety limit somewhere within the electrical field of 7 volt per meter. Effective radiated power. As a reminder, these are the equations we are going to use for the calculation of ERP. And this is a table we use to bring PT, transmitted power, and the gain to calculate the power density, and hence we end up to ERP. We computed and simulated ERP across a range of distances from antenna R. And for better visualization of results and presentation, we split the graphs into 2 parts, from 20 to 100 meter. This is the distance from antenna, and from 1 to 20 meters. As you can see, the first observation is effective radiated power is unique for each frequency. As you see the result here. The second observation is electrical field decreases with increase of distance. Another observation is if we compare this graph against this graph, we notice that as we go closer to the antenna, we see a sharp increase in the electrical field. For instance, here at 2 meters, at this point, it's around 140. When we are at 1 meter, it sharply increases into 270. However, here at 30 meters, it's around maybe 9 volt per meter. And at 10 meters, I mean, we close 10 meters, it increases only to 14. So here we have, in this graph, we have sharp increase. We made a comparison of SAR across different literature, and this is the table. This is the referenced SAR, and this is our SAR. You can notice that the values are almost close to each other. However, our values are slightly higher. The reason behind probably refers to the fact that different crowd scenarios used in different literatures. Thanks for your attention.